Hello, everybody. This is also going to be a very, very interesting one. Allow me to introduce to you Vasilios. He's a research engineer, and he's going to be presenting to us how to measure actually the internet with Python. So please welcome him, and thank you very much.
Hi, everyone. Thanks for the introduction. So I'm Vasilis, and it's great to be here. Although I'm from Athens, it's the first time I'm speaking in Athens. And before I begin, a big shout out to all the volunteers who are responsible for this organization, because it's really great. I hope it will continue in the next years too. So today I want to explore together how we can measure the internet with Python. And by the end of this talk, I hope that you will take away some of the core tools that we have available, open data that we can find and measure the internet, and how we can stitch those things together into real-world measurements. So a couple of things about me, why I'm interested in this topic. So I'm a senior research engineer in Cloudflare, based in London. And I want to describe my work as trying to make the internet better, right? So my research focuses on making it more resilient, more secure, and more efficient for users. I also have roots in academia. So I did a PhD in this very topic, mapping the internet topology. And I am also a visiting professor at Lancaster University in the UK. So if you want to access the slides or the Jupyter notebook that has the code in this talk, please scan this QR code. This website was developed by my son. I have no idea about website development, but he did it in a couple of days. So why measure the internet? Here you can see in this image the Cloudflare network. It's composed of hundreds of data centers all over the world. It's a really large network, very hard to monitor, but it's very important to monitor because we need to be able to find problems fast and address them before they bite. We need to ensure that our users enjoy the best performance and that there are no weird detours. We need to make sure that it's reliable, so if something fails, it doesn't affect the other parts of the network. And importantly, we need to inform the work that engineers do or support or even policymakers with hard evidence. And the policymaking thing is important because regulators and policymakers take a special interest on the internet. In many countries, they want to control it in many different ways. So we need to inform them with actual data, because quite often they don't have this data-driven view of the internet. There are also many other use cases beyond operational purposes. And I would say that the internet is so fundamental in our daily lives that whatever your area of work is, be it humanities or law or engineering or anything really, internet measurements can give you interesting insights, right? So I'll start with a small background just to make sure that we are all on the same page, and then I'll go to the more Pythonic stuff. So what is inside the internet? So when we say measure the internet, what am I referring to? Typically, you see some visualizations like that, where a user connects to a web server, and there is this abstract cloud. So what's inside this cloud? We don't connect directly. We don't have a single cable that takes us there. That would be awesome, because that would be very fast. But we have to go through a lot of different hops. These are these router devices. We have one small at home, but the path goes through these carrier-grade routers. And each router has many different network ports. Each port uses an IP address. So we can abstract this path as a series of IP addresses, right? And this is what we want to discover when we say we want to map an internet path. We want to map the series of IP addresses that we should follow. Now, we know that we need to reach a destination with a specific IP address. Typically, we use DNS to resolve a domain name. But how can we get the IP addresses in between? To do that, we piggyback on a simple mechanism that every packet in the internet has called TTL, time to live. You can think of it as a countdown timer. Whenever a router receives a packet, checks TTL, decrements it by 1, and pushes it forward until it reaches the destination, or until TTL goes to 0, and then the router will send it back to us and says, your TTL expired, do something else, like increase TTL or give up, but I cannot forward it further. And this is important because, like that, we avoid packets being tossed around aimlessly in the network if there is a misconfiguration. But we can take advantage of this functionality to map the internet. So the idea is that we start sending a packet to our destination, but with a TTL of 1. And like that, the first hop will respond back to us, and it will say, on this router, your packet expired, take it back. And when they reply to us, they have to include the IP address. So we know the IP address of the first hop, and then we increment TTL by 1. So the second hop responds, and we get its IP address, and so on and so forth. We incrementally increase TTL until we map every hop in the path. And this technique is called traceroute. Every major operating system has a tool called traceroute that does exactly this thing. So here I have an example of a traceroute that I run from my laptop to example.com. And you can see we have a sequence of IP hops and the round trip times, so how long it takes for traffic to go from my device to this hop and back to me until it reaches the destination. You can also see that we have some asterisks, which are hops that did not respond to our traceroute probes. And this is a common limitation because routers have a lot of important things to do apart from responding to traceroutes. And quite often they make it the list of their priorities. So they may not respond. They may consider it a security threat to reveal themselves. But despite that, we can still get very useful information on the path, even with these holes, right? But enough with these command line tools and the introduction. We are PyCon. And here is how to build a traceroute with Python. So there is this very nice library called Scapy. And Scapy lets us build, craft, manipulate, dissect network packets, right, with just a few lines of code. So in this example, I am creating a loop. This loop increments TTL from 1 to a max TTL, 20 in this instance. And then I am crafting an IP packet with the destination that is example.com. And the TTL of its loop, of its iteration of the loop. Then I wrap it inside a UDP packet. Scapy has this very nice way of chaining network packets with this backslash. So you create an IP packet, backslash UDP, you put it inside a UDP packet, and we define a random port. So now we have our packet. We send it with this SR1 function, means send, receive one packet. We will wait for 2 seconds in case you encounter one of these asterisks, right? The router doesn't reply. And then that's it. The only thing left to do is to parse the response, right? So here's how we parse the response. This is slightly more involved, but really simple as well. Essentially, we check if the reply is none. If it's none, it means it times out. OK, we don't care about it. If it's not none, we check if it has the ISMP protocol. ISMP is the protocol that is used for these expiry messages. If it does, we calculate the round trip time by subtracting the send time with the receive time. We check the code of the message. If it's a time exceed, it means that we discovered an intermediate hop. If it's a port unreachable, it means that we've reached our destination. And yeah, that's it. Essentially, we have a traceroute tool with just a few lines of Python code. It's that easy. So now that we have our traceroute path, our sequence of IP hops, then we can go and level up our measurement capabilities, because now we can go and we can geolocate those hops and find the geographic route that is followed by our traffic. Again, very easy to do with Python. There is a library called IPGeo2, which is an API that reads a type of database called MMDB. MMDB is a format which is optimized for IP lookups, developed by this company MaxMind. And it's very easy to find MMDB files because there are a lot of IP geolocation companies that make them publicly available. There are also commercial datasets, but the publicly available tools are good enough for most purposes, so you can find them either from MaxMind or IPInfo or IP2Location. And then it's super easy. You create a database reader object, you feed it the database that you downloaded, and you just iterate through your IPs in the traceroute path. For every IP you query this database reader, you get the city name, you may get the country code, and here you see that in this example, we've geolocated the path from our device to example.com. It goes through from Athens to Frankfurt, Ashburn, all the way to Los Angeles, right? So just be careful with taking those geolocation at face value, because IP geolocation tends to be inferential, meaning that it can be wrong. You can use it as a broad view of the geographic path, not as a street-level view of the path. So yeah, so we did it. But what have we done? We just measured a path from our device to some other device on the internet. This is not measuring the internet, right? This is just measuring our connection. Not so interesting. We want to map the large-scale view of the internet. And to do that, we need multiple vantage points. We need to measure the internet, not from our device only, but from many different devices spread all over the internet. How can we do that? There is a really incredible platform called RIPE-Atlas. RIPE-Atlas, essentially what it does is that it crowdsources some Raspberry Pi devices that we call probes in this context. So there are people who are passionate about measuring the internet, and they sort of say, okay, yeah, I'll host a probe in my network. They plug it in the router, and these probes run trace routes, pings, DNS measurements, HTTP measurements, the whole thing. And the best thing is that the data are becoming publicly available. Everybody can access this data. And it's a global platform. It's this figure is from yesterday. There are more than 13,000 probes all over the world. You can see that there are some regions that are not as well covered, but we're working on expanding this platform. If you want to contribute, you can also host a probe. Just go there and request either a Raspberry Pi probe, or there are software probes. So we can use any of these green points to run exactly the measurement I described before. And RIPE-Atlas provides several ways to interact with it. It has a point-and-click web interface. It has a RESTful API. Most importantly for us, it has Python libraries. It has 2 Python libraries, RIPE-Atlas Cousteau, which is a wrapper around this RESTful API, which makes it very easy to create measurements, and Sagan, which is a parser for the results. So let's see how easy it is. This is all it takes to run a distributed traceroute from whichever location we want around the world. So here I just create a definition of a traceroute measurement. I say, target is example.com again. I want TTL to be 20, protocol UDP. Then I pick my sources. In this case, I was conservative. I said, give me 15 probes globally distributed. WW means worldwide. I could say a country code, GR, and I could say, give me 100 probes from GR. I can have multiple Atlas source objects and combine them, so I can craft many different country footprints. And then I feed these 2 definitions, the traceroute and the Atlas source, into an Atlas create request object. I give an API key. You need an API key. You can get it for free. Just register yourself in the website, and it's nothing. And then we call create, and that's it. You created a distributed traceroute test from 15 globally distributed probes. And we can go in the RIPE Atlas interface, and we can see our measurements. We can see, for instance, in the map here, which probes have been selected, the round-trip time, and some overview of the results. We can see the detailed results, but again, we want to do it in Python. We don't want to do it with this web interface because let's assume we have thousands of such measurements, right? Which is exactly what we have in most of the time. We want it to, we want programmatic access. So again, super easy. We get the measurement ID. We feed it to an RIPE Atlas, an Atlas request object, and we get the JSON, which is containing the output of this measurement. Now, a small problem is that this JSON is very complex, and this is where another RIPE Atlas Python library shines, Sagan. Sagan makes it very easy to parse this JSON code because it provides a nice, clean interface that exposes some easy-to-use objects. So, for instance, you can access easily attributes like the IP address or the round-trip times. You just take the raw JSON, feed it in a traceroute result object, and then it exposes, let's say, the median RTT, the TTL, the IP address of a hop, and so on. So you can see that I recreated the output of a traceroute of the traceroute tool with just a few lines of code, right? So, with less than 30 lines of code, I have a distributed traceroute measurement that I can then process. Right now, so far we've mapped the IP level path from a device, either our device or these RIPE Atlas devices, to the rest of the world. But a question that we often have is who owns these devices, who operates them, who deploys them? And the answer is that the internet is not a monolithic network, right? The internet is a network of networks, so it's composed by thousands of individual networks called autonomous systems. And these are networks like an ISP, like a university, like a cloud provider, which interconnect with each other in order to enable this global reachability. Each autonomous system has a unique AS number. So for instance, in this example, our path goes from OTE, a major Greek ISP, to Aurelion, which is an international transit provider, to Akamai, which is a CDN. And we can abstract the path just to the AS level hops. And this is, if I use a metaphor, if the IP level path is the street level view of a route, the AS level view is the satellite view, which is also important because it gives us the chance to look at some macroscopic properties of the internet and look also at the business relationships that dictate how traffic flows. Now, how do ASs decide how to route their traffic, how to pick their paths? Sky News did a nice segment on that a few years ago, and they said BGP is the GPS of the internet, right? The protocol that AES use to route traffic is called BGP, although they called it the bridging gap protocol for some reason, although it's called the border gateway protocol, and I'm not letting this blender die out. So how BGP works? BGP works like word of mouth. So you have an autonomous system, like A7 here, that has a prefix, and it wants to say to its neighbors that you can access these IPs. A prefix is a set of IPs, right? You can access this set of IPs through my network, and it will send this message out. This is a BGP update message. The neighbors of this AS will take this update, will create a routing table, put in this information, and it will propagate this information to their own neighbors, and so on. So this information will go through the network, and at some point we have AESs, autonomous systems, with more than one route. So the path selection process on the internet, some may think that, okay, shortest path wins, right? Wrong. On the internet, it's policy-based routing, meaning that an AES says, for me, the most important thing is economics. I want from my traffic exchange to make money before making the path efficient. So I will pick the path that generates profit. And how does a path generate profit? So when these autonomous systems interconnect, as I said, these are commercial entities. These are businesses, ISPs, cloud providers, and so on. And they don't exchange traffic just because they are altruistic. They do it because they pay each other to do so, right? So this is another reason why we are interested in measuring the BGP view of the internet, because it gives us these unique insights into the economics of this global network. And fortunately, we are also able to measure BGP because autonomous systems give routing tables to some public BGP collectors with the purpose of making it easier to debug routes. So when the internet started, everybody figured out that BGP is so complex that they create a policy. This policy did something different than what they expected. So they said, OK, let's make these routes public so that we can look at each other's routes and figure out what's wrong. And we can do that too. There are two major projects that collect those BGP paths, Radius and RIPRIS, and they provide real-time access to the BGP tables of backbone autonomous systems, which is really cool. So this is a massive data set, and we can also parse it with Python. There are a few different Python libraries to do so. I like BGPKit because it's very fast. It's written in Rust under the hood, and it has a Python sort of module that is a wrapper around it. It's a port. And it's very fast, which is important because these BGP data are massive. We are talking about terabytes of data. You can think of these massive BGP routing tables from international AESs. So we just create a broker object. We say the time, the start and end time, the names of the collectors, and then you just, then it's simple Python. You just get an element that exposes some properties like AES path, prefix, and so on. So here, for instance, in this very short Python code, I measured the total number of AESs and the total number of AES links, 55,000 AESs, 180,000 links, right? It's a big network. And we can use also this data to map the IP hops in the trace route to AESs. There is this nice Python library called PyASN. You feed it a BGP table. It creates a database that maps prefixes to ASNs. It's based on a PyRadix tree, and 3 lines of code. I've mapped 888 to Google. Now, I've covered a lot so far, but there are much more. There are many open data sets that provide RESTful APIs. They don't have a Python library. Maybe you can go and build one, but we can still consume these APIs with requests. So here, for instance, I'm querying the RIPStat API to get all the ESs that are registered in Greece. And we see, as of today, there are 248 ASs. Yeah, so I think it's time to land this plane now. Let me summarize what we saw. We saw that we can map the path from our device to a remote server using SCAPI. We can geolocate it using IPGeo2. We can run globally distributed measurements with RIPE Atlas. Then we can go to the ACE level view of the internet with Radius and RIPRIS using PyBGPKit, map IPs to ASNs with PyASN, and query REST APIs with requests. So to conclude, if you find this interesting, there is a very nice free online course on internet measurements that will guide you through this whole ecosystem. You can volunteer your Python skills. These are all open source projects, and they do want developers and maintainers and people with fresh ideas. You can create cool visualizations of the internet, of things that you care about the internet. You can host, of course, a Padlas probe and join a management hackathon. I think the internet is a public utility. It's often seen as a black box, but it should be transparent. It's important to have transparency on the internet because it's important for equity of information access and equality. So yeah, if you'd like to contribute, that would be great. Ideas, feedback, questions, anything you need, feel free to email me or ask me now. Thank you so much.
What a great one. That was actually very insightful. Thank you very much, Vasilis. It is now time. If anybody wants to shoot any question, please feel free to do so, folks. We got one.
So thank you. That was a great.
Thank you very much.
Yes, a great session. So my question has to do with the, let's say, impact of this work. So you said something in the beginning. So you, let's say, have a big map of the internet. Who actually, let's say, cares for this? It's, let's say, can you help governments?
Yes, this is one of the most frequent things that we do. Yeah. There are a lot of governments and a lot of international organizations that have certain ideas about the internet, about how the internet should work, how the internet should be siloed. And usually these come from misconceptions about how the internet works. So with this data, with these maps, we often go, not as like operators, but also as academics. We go to the European Union, we go to governments, and we say, look, this is the internet, this is what it needs to work correctly. If you remove this node or if you restrict this connection, it will have impacts that you probably didn't realize, but we can show you through a simulation, we can show you through a data-driven analysis. Yes, and it's in terms of informing policy, it's one of the most frequent use cases that we have. It's
okay, I see. So, okay, what, let's say, when we say remove a connection means like Brexit, war, or something else?
Let me give you an example. Quite often, governments request that, let's say, certain data should not go outside of a country, or certain data should not go inside the country. And to do that, they set up firewalls, they set up deep packet inspection middle boxes that would filter traffic, and they would probably require to put data centers only in a certain country. And they think that like that they protect the internet, for instance, of this country, but in reality they make it more susceptible to localized failures because you don't get the failover connectivity that a rich internet has. And that's just a recent example that we were communicating with certain governments about it.
Great. Kudos to you. Thank you very much.
Thanks so much.
We also appreciate you for the great shout out at the very beginning. Thank you.
Yeah, it's amazing.
And the feedback.
Awesome work.